Hi, everyone. My name's Dr. Jason DeVoe. I wish I could be there in person to deliver this to you, but sometimes life gets in the way. So, today's lecture is about aerial off-target pesticide movement. You probably all know this is drift, and we'll get into it. But I just want to challenge you before we start. I mean, it's hard enough to hear a guest lecturer in person, but wow, listening to a pre-recorded one, you could just drift off yourself. But ching. So here's the challenge. I just want you to try to remember three things, any three things. It doesn't matter. And at the end of this lecture, I want you to highlight, write down, or submit to David, Dr. Hooker, the three things that you took away from this. There's the challenge. All right, let's get into it. When we talk about pesticide contamination or pesticide movement, there's a lot of ways it can get from where you would have liked it to have stayed to where it ultimately ends up. And we can call all of this collectively off-target contamination. As I mentioned, the one everyone's most familiar with is drift, and that's pesticide traveling through the air to where we don't want it to go. It is direct off the nozzles at the moment you sprayed, or insidiously, it can be long after you've gone home when it comes off of those sprayed surfaces. But there's more ways product can move where we don't want it to go. Point source contamination, we just don't talk about it enough. And this is pesticide coming from the inside of the sprayer itself or from the outside. It could be leaky storage of pesticides. It could be residue or what we call carryover, the last thing you sprayed sort of lingering to the next spray. It could be spills while you're filling, happens a lot. Or rinseate. When you're being good about cleaning the sprayer, what do you do with the dirty dishwasher? Or priming. Well, you don't just start spraying from a 120-foot boom. You've got to squeeze all the liquid to the furthest nozzle, and that means you sit in one place spraying until you know it's charged up. And there's also environmental contamination after you've sprayed, like surface runoff. Rain can take stuff where we don't want it to go, right into the water table, right into a river or lake. There's also atmospheric contamination. Believe it or not, tiny amounts of pesticide have been found in Arctic ice and remain airborne a long time. And when it rains or it gets caught up in the precipitation cycle, it can go quite a distance. Even contaminated dust blowing around is a source of contamination. So, again, this is kind of where we're going to focus today, but I always like to put all this in text. And the reason I like that is this histogram. This came from a group called TOPS, I forget what the acronym stands for, at a meeting in 2019. And what they did, a number of countries, how would I say it? They counted up all the places that contamination could come from. And they said, okay, if there's 100% contamination, that is to say, here's a tally of all the things that contribute to contamination, how does that break down? Well, 40% of what they found was runoff. Now, admittedly, in Europe, runoff is a much, much bigger deal than it is in North America. They don't have the Great Lakes, unfortunately, so anything that runs off the surface of their soils tends to end up right in their drinking glass, and they're pretty bent out of shape about that. Point source makes up 55%. That's things like filling or cleaning. And then, of all the off-source contamination that they could account for, only 5% is actually drift. So it makes you think, why are we focusing all our attention on drift when 95% of it isn't drift? And it kind of gets worse. Point sources, that 55%, no problem. With the right technology, we can eliminate that entirely. One day, look up closed transfer. You'll like it. As for runoff, that can be reduced by 50 to 70%. But drift can be reduced by 70 to 90%, but never entirely eliminated. So if the best we can do is 70% of 5% of the problem, I don't know. But they keep asking me to talk about drift. So let's do it. There are two kinds of drift. This can be argued, but it's a nice way to think about it. The first, we'll call that primary movement. While you're spraying, that's what's happening right there and then as you're spraying. It's the initial Mechanical movement of droplets, usually caused by wind or turbulence. They simply move off course. And it's a matter of meters. And then there's the secondary movement I alluded to. This can happen long after you're done. It's delayed, and it can take a long period of time to occur. And it's entirely based on the molecular structure of whatever chemical was applied. And when it moves, we're talking kilometers. So let's dive into the first one, the primary movement or particle drift. I'm sure you're all rolling your eyes at the moment. Yeah, we get drift. We've lived on the planet. That's how we think about drift. You take a small droplet, you add wind, you get drift. Now that leads us to think wind is bad. But I just want to tweak your imagination for a moment. Einstein used to do things called thought experiments. Basically, he just used his imagination, and we're going to do that. Imagine, if you will, that you're holding a golf ball and a ping pong ball in one hand. The golf ball is, we'll say, an extremely coarse droplet. It's the biggest thing your sprayers would make. Whereas a fine or a ping pong ball is a lighter, smaller droplet. Both can be created by a sprayer, no problem. Now, I'd like you to turn into whatever light wind you happen to be standing in and just toss them up into the air. What's going to happen to the extremely coarse droplet? And what's going to happen to the fine droplet? Well, it doesn't take a Einstein to figure this one out. The coarse droplet is going to move ballistically. It's going to kind of go up into the air, and it's going to move in the direction of travel, and then gravity is going to say, hey, what are you doing up there, and haul it down. It's going to move in a straight line unless something happens to interfere with it. Whereas the fine droplet, the ping pong ball, it depends. The government answer. How hard did you throw it? How windy was it? How high did it go? Maybe it'll end up in front of you. Maybe it'll blow behind you. So let's pick them back up, go back to where we started. And this time, we're not just going to toss them lightly into the direction of the wind. We're going to haul off and throw them as hard as we can. This is analogous to increasing the pressure behind a nozzle. Maybe we can get a droplet to go where we want it to go by really putting the pressure to it. Now, the golf ball, we may never see that again depending on how good your arm is. But it's still going to move ballistically, in a straight line, arcing up, falling down. The fine droplet, or if it's easier for you, imagine throwing a feather. It kind of doesn't matter a whole lot. Obviously, if you add enough pressure or enough force, sure, you can throw a feather, but it's a wild amount of force, and it's well outside reason. So basically, no matter how hard or how much pressure you put behind a fine droplet, it's really not going to affect anything. Now, what does this matter? I'm sorry for the big table, but we're going to focus in. On the left-hand side, where it says particle diameter in microns. That's how big your droplet is. Top left is 5 microns, bottom is 1,000 microns. In the next column over, these are just common descriptors. A 5 micron droplet is by definition fog, whereas a 1,000 micron droplet is a pretty good rain you don't want to get caught in. Let's look right here. Let's say we had a 50 micron droplet, that's the top arrow, and a 200 micron droplet. The difference is misty rain and light rain. And let's say we stand on a ladder and just, if we could, drop these two droplets. How long would it take for them to fall 3 meters in seconds? Well, the smaller misty rain droplet would take, if this was possible, 40 seconds to fall 3 meters. The larger droplet would take 4 seconds. Now let's say there's a light wind while you're doing this. How far downwind will the droplet go before it hits the ground? Well, that 50 micron droplet will take 40 seconds, we said, and in that time, it'll go 53 meters downwind before it hits. The larger droplet, well, it's moving faster. It's going to hit the ground sooner, so 6 meters. Now, this is, again, kind of a thought experiment. This takes very specific conditions and a lot of models to figure out, but it is representative of droplet behavior. Also, since we're talking about reality as best we can, we have to consider that these droplets aren't just going to remain intact all this time. Think of them as steaming as they're dropping. It could be a hot and dry day, and water has a tendency to evaporate. In fact, for that 50 micron droplet in a certain heat, I think it was 32 degrees and relatively low humidity, it'll actually evaporate into a little bit of dust in about 7 seconds. It won't survive the 40 seconds it would take to fall. Whereas the bigger droplet, they can stick around for more than 30 seconds. It'll have long hit the ground. So you begin to get a sense of how droplet size affects behavior and affects droplet fate and how that might work with drift. So let's reconsider that original idea about what makes drift. What actually causes it to drift? Was it the wind? Or maybe it was the size of the droplet? So let's look at it this way. Imagine we have a low energy situation, a droplet that's moving very, very slowly. And then we expose it to some force, I don't know, say wind or turbulence behind the sprayer. Well, we get movement. And what we see now is it's not just the force or the wind that plays a role, it's the energy state of the droplet. Is it a great big thing that's falling like a rock, or a very small thing that can be moved around a lot? When we think about it that way, we can start to think about how we might drift or greatly reduce it. You can never entirely eliminate drift. So let's look at droplet energy. One way to change the equation is to increase the droplet's energy. We know we can make it bigger or we can move it faster. We've established that. And in reality, here in real life, we can do that by using a low drift nozzle, which makes droplets much bigger, or we can boogie it along. We've learned pressure maybe isn't the best way to motivate a droplet, but maybe using air for good instead of evil is the way to go, and we can use air assist to blow the droplet in the direction we want. The other part of the equation was the exposure to force. Why don't we reduce the amount of force that a droplet is exposed to? We can protect it from wind or turbulence by shrouds or similar. We can decrease the time that it's in the air moving from A to B by maybe getting the nozzles closer to the target. Pretty neat, huh? Oh, come on now, it's fun. Okay, you're doing well. Part two. Now let's talk about droplet size in regards to the nozzles and the pressure. We've already started to nudge this. I did this on AI. I'm very proud of me. I've drawn this so many times over the years, and it always looks like what it is, like a child tried to draw it. But thanks to AI, I can tell it what I want it to draw, and it can get it wrong. But if you do it often enough and nudge it enough, you do end up with something pretty cool. So how do we talk about droplet size from a nozzle head's perspective? We use terms to describe what actually comes out of a nozzle. For example, if you get a nozzle and you bought into what I was saying earlier and you go, you know what, I want a big enough droplet that I don't want it to blow all over the place. I'd like a nozzle that produces a droplet that's 500 microns, please. And you go to the store and you ask for this, and they look at you like you have a carrot growing out of your head because there's no such thing. But they can say, I don't have that, but I have a nozzle that's rated for what's called coarse. That's a droplet size. And you say, okay, that sounds like it won't blow all over the place. I'll take one of those, please. And you get home and you put it on your sprayer and you look at the spray and some of it blows away and you think, I'm going back because I kept my receipt. Well, actually, hold on a second. What's actually happening here is the nozzle's behaving the way all nozzles behave. Just because it said it made a coarse droplet doesn't mean they're all coarse. It's actually an average or near enough. And this is what this illustration is. Look to the top right. That normalized bell curve, that shows all the different droplet sizes that a nozzle can produce. On the y-axis, that's the one that's vertical, there's your volume distribution. And on the x-axis is something called VMD, or volume median diameter. And this is why this illustration was always tricky for me to make. It's not really the average droplet size. What it is if you imagine your nozzle sprayed into a bottle and it didn't spray water, maybe it sprayed actual particles like marbles or rocks, and you just collected everything that came out of it for a minute. And then you were able to sort all those different sizes. Well, half the volume that the nozzle spit out will be comprised of big droplets, and half the volume that the nozzle spit out will be comprised of smaller droplets. You just sort them out. Whatever size droplet represents the middle of that is the VMD. 17 years I've never been able to explain this quickly or easily. What size droplet is it where half the droplets it produce, or sorry, half the volume is smaller and half the volume is comprised of bigger? That's what this illustration is supposed to show. I don't know if it did it. I wish I could see right now to see if you were wildly confused or not. But that's the intent. All nozzles produce a range of droplet sizes at a single pressure, and the volume median diameter is the droplet size where half the volume is smaller, half the volume is larger. There, I'll stop beating that horse. So when you bought your coarse nozzle and you thought, hey, I'm bulletproof, here's the bad news. Because there's a cubic relationship between droplet size and volume, you may not be getting what you think you paid for. Now, what am I talking about? Imagine you have one large droplet. It's 200 microns in diameter. How much volume is in that droplet to make 100 micron droplets? In other words, it's 200 microns. How many 100 micron droplets can you make out of that ball? The answer is 8. It's a 1 to 8 relationship. That's a cubic relationship. So every time the droplet size average falls by half, the number of droplets you have goes up by 8 times. And here's what we're looking at here is a different way to look at what a nozzle produces. That little yellow thing, that's water-sensitive paper. I love water-sensitive paper. It's just a little yellow card, and when you spray and pass over it, wherever a droplet lands, it turns blue. And I get the enviable job of counting them. But it does tell you how many drops that a nozzle will produce or land. And if you've got the right software, it gives you their relative diameters too. And that's what we have here on this graph. Diameter at the bottom, droplet count on the y-axis. The DVO5, or the VMD, that volume median diameter, is 390 microns. You can see it there just under the card. But look how many droplets produced are smaller than that. Amazing amount. There's only a few really big ones, but just a wild number of small ones. This is why you can never eliminate drift. Even if you get the coarsest nozzle going, it's still going to produce anywhere between 2 and 5% of his volume based on tiny, tiny droplets. So here's what that looks like. Here's a nozzle that claims it has a volume median diameter of medium. I think that's like 300 microns. And you can see that it's actually producing a range of droplet sizes. On the horns, or the edges of the spray, they're much coarser. They're also moving a lot faster. In the middle, you know what? I wonder if I can show that again. Will you let me go back recording? No, I won't. Well, sorry about that, guys. In the middle, you should have seen, I hope you saw, that there were finer droplets moving slower, and on the edges, coarser droplets moving quicker. This is why we have multiple nozzles on a field sprayer and why we want them to overlap. That way we get a nice homogeneous mix of bigs and smalls. All right. So when you're picking a nozzle, if you're trying to avoid drift or do a good job, you're going to get overwhelmed by all the nozzle choices. They're gorgeous colors. It looks like candy to me. But what I want you to really look at here are the symbols. XF, VF, F, M, C, VC, XEUC. These are the volume median diameters, or the spans, or the droplet sizes produced by a nozzle. And here are the ones I never, ever, ever want you to use unless you're in a greenhouse. You don't ever want to use droplets this small. They're just not controllable. They evaporate really, really quickly, and they blow all over the place. It's the larger stuff. That's the stuff we can predict where it's going. Now, if you get too big, it's just a raindrop, and it's going to hit the target. Maybe. That's a lot of spray tied up in a single droplet. So you want them small enough to hit everything, but big enough to stay on course. Wow, I know. That was a tough one. It gets easier from here, I promise. Let's talk about how somebody might set up a sprayer and use it to minimize drift and optimize. Here's the first truism. Trying to catch drift is kind of like putting the horse in the barn or closing the barn door after the horses run away. I always love that metaphor. I guess it's a simile. Never mind. So, using things like buffer zones and windbreaks, we need to. They're important. But honestly, the best way to reduce drift is just not to make it in the first place. This is where how you use your sprayer comes into it. High speeds and high booms, often you see both of those at the same time. The reason is because as you drive fast, the boom bounces up and down, and we don't want it hitting the ground. So an operator that drives quickly tends to raise the boom a little higher so they don't smack it off everything. Now, this picture comes from Dr. Tom Wolfe out west. I like to call this prairie speed, and then he gets angry at me because it implies that everybody out west drives this fast. But this is a singular moment, we'll say. This operator's flying along at 25 miles an hour. And you can see that a lot of that spray hasn't landed yet. A lot of that is because wake and turbulence play a role. Just like a speedboat going through the water and leaving a wacky wake behind it, a sprayer driving through the air creates a wake as well, especially around the chassis, that's the body of the sprayer, the wheels, and even the tips of the boom create vortices as well. So, driving fast and being in a headwind are essentially the same thing. And when that happens, the smaller droplets get sucked out of the swath. So, a number of years ago, I guess Tom was bored. He decided to go out into a field with a bunch of students and run a long length of fishing line across the ground, just suspended it a couple of feet off the ground, and then drove a sprayer over it spraying dye. And then they picked up that string and they cut it into little pieces and analyzed how much dye they could find. And all this to say it was a way to describe where the spray went under the sprayer. And that's what you're looking at here. That graph of red is how much dye they found directly beneath that sprayer. And for a boom that was 40 inches off the ground, that's a bit too high, by the way, and a speed of 17 miles an hour, that's a bit too fast, by the way, and a medium drop, that's a bit too small, by the way, you get this jagged line. And it's defined by something called CV, coefficient of variation. It just means how wacky is it. This is pretty wacky. That's not something anyone wants to see. You get like less than 50% of the deposition around the wheels. You can see the two depressions right in the middle. And then it kind of gets higher up around the middle of the boom. And then you see, it depresses again on either end because of the vortices created by the tips of the boom. All this to say, not too good. A CV of 38% means it's 40% not good. So, we know if we drop the boom and slow down and go to a bigger droplet, it should get better. Well, we left medium droplets because, we still wanted to see something goofy here, but definitely lowering the boom from 40 to 24 and slowing down to 7.3 miles an hour got us a more reasonable coefficient of variation. If I'm honest, though, that's still not great. A coarser droplet would have helped. So, what could we do with the sprayer? Well, people might want to make their booms longer so they can do fewer passes, and that saves some time. But then it gets really tippy. That's great. Again, one of Tom's favorite games in the world is playing chicken with sprayers. He likes to stand right in front of an oncoming sprayer. Not something I'd recommend, even if you're a limbo champion. But he's been trying to capture a level boom for most of his career. And here's a photo of this thing bearing down on him and an obvious slant to the boom. And then moments later, there it is slanting in the other way. And I can only expect Tom dove out of the path at this point. He has done some very cool work trying to prove that mitigating drift isn't just an environmental thing to do or you know, save your neighbor from getting hit by a pesticide thing to do. It's also an economic thing to do because any pesticide that's drifting out of an application is not doing what you paid for. You want it to land where you want it to land. So take a look at this histogram for a second. We'll break it down. On the left, those two bars, they show how much hits the target if the boom is low and the speed is slow. On the right, if you speed up and use a higher boom, There's how much spray lands on the target. You can see at the bottom we have a medium droplet size and a coarse on the left, and then a fine, medium, and extremely coarse, which is quite large on the right. And it means that if you just slow down and drop your boom a bit, you can get 10% more spray where it's supposed to land. Even using that extremely coarse droplet on the far right wasn't enough to take care of the high boom and fast speed. Ooh, I think I just answered my own question. Can a coarser spray quality compensate? Can bigger droplets help? I don't know. I think we all know the answer to that. We'll call it a gimme. Uh, Here's another way to look at it, though. There's airborne drift at the left, the vertical bar, and at the bottom there's your wind speed. So let's say we're using a nozzle. This is a Turbo T-Jet 11005. It's pretty classic. You know, it's nothing to write home about, but you're using it on a boom that's 30 inches off the target. And you can see that as the wind speed increases, then the amount of airborne drift increases. That's why it's going low to high. The higher the wind, the more drift. If we switch over to a nozzle that gives a bigger droplet, this is an air induction droplet. It just makes bigger drops. I'm sorry, nozzle, I should be saying. The T-Jet air induction nozzle makes bigger drops. It's the only change we made. The boom's still 30 inches off the ground. Well, if the wind is 14 miles an hour, we've just given ourselves a twofold reduction in drift. That's pretty amazing, just in changing to a larger droplet. If we also drop the boom by 20% and slow down, well, at 8 miles an hour, now it's a fourfold reduction in drift. So they work hand in hand. Slowing down, dropping the boom, slightly larger droplet, big savings in drifts, and much better coverage. And if I still haven't convinced you, I don't know if you've noticed this, but occasionally Canada gets snow. And while my favorite thing to do is look out the window and wait for it all to go away, sometimes I get ideas. So I had this idea that we could fill a little handheld boom sprayer with rhodamine, a pinkish red dye, and go play in the snow. And we did. On the left, we have a boom that I'm going to say is at the right height. It's close enough to the ground that all the nozzles overlap and you get nice even coverage. And then in the middle, if I hold it too close to the ground, those three nozzles don't overlap and you end up with too much, not enough, too much, not enough. And if you lift it too high off the ground, that's the right. I just leave it to you to guess which way the wind was blowing. So low and slow's the way to go. And I kind of like spraying in the snow. Drift reducing technologies. What else can we do besides how we set up the sprayer and getting a bigger droplet? Well, we can decorate our sprayer with shrouds. Um, this is this is what everyone says is a technical truth, but I'm willing to bet nobody in this room has ever seen a sprayer with all these shower curtains hanging off of it. And hey, don't get me wrong, it works. It also weighs a ton, causes the boom to drag in wind, and you tell me if you've got a plug nozzle. So I'm going to say it's not a very practical way to do business unless it's a really specific application you're chasing. On the other hand, I like air induction. I'm sorry, I like air assist. This is a sprayer with a blower built right in. You see that big long black arrow that spans the two pictures? That's a 13-kilometer-an-hour wind, and it's blowing from the tractor past the sprayer from right to left. Now, this sprayer has air assist. It makes a curtain of air. If the air is off, that's on the left, you can see that this parked sprayer, the spray is just blowing in the direction of the wind. But on the right, if you turn the air on and it blows that curtain of air sort of into the direction of travel, you can see the spray's moving in the other direction now. So if that sprayer was moving, it would pretty much look like it's going straight down and nothing would escape that air curtain. And I love them. They're brilliant. Not only do they keep spray moving on target, they also flip the crop around. They expose all of its surfaces and they open holes in a canopy that spray could otherwise have never have found its way into. And yet, we don't use them. Why? 'Cause they're expensive. Well, that's part of the reason. Mostly because I think on larger sprayers, people spray herbicides probably more than they spray fungicides. And you don't want to be using air assist unless you're spraying into a canopy. That canopy gobbles up all the velocity, the air, the energy that's created. Back to how we started this talk, it's a lot about the energy. And if it's just bare earth and you're doing a pre-emerge herbicide, well, you're going to ricochet that herbicide off the ground, and ain't nobody like that. So when you consider the expense and consider that it's really only good for fungicide, perhaps insecticide applications, North America never really ran with this idea. What of drift reducing adjuvants, you may be asking? I bet you're not, but I'm going to pretend you are. Some people are of a mind that if you drop magic into the tank, drift goes away. And I mean, I don't want to be so dismissive of it, but I do question people hitting the easy button without really thinking about it. There's no doubt that anti-drift adjuvants can help reduce drift. In this case, this is interlock. It's one of many different options. On the left, that misty nightmare, similar to what I showed in my slow motion image. You can see the coarser droplets on the edge and the finer stuff in the middle, and the finer stuff in the middle blows away. But if you add interlock, what it does is it almost like taking a bunch of little snowballs and packing them together into larger snowballs. It just mushes together all the fine droplets that a nozzle creates and makes them larger. And the cool thing about it is it does it without making a lot of extremely coarse droplets. It just kind of takes out the tailing end of the span, and it works. But it is the last thing you do. Boom height, travel speed, and droplet size, and of course knowing what conditions to spray in, all of them have so much greater impact. If after all that you still think, I don't want this to drift at all, then go ahead. You can throw an anti-drift adjuvant in, but it's not going to save you from doing all the rest of it wrong. Now, a lot of that, all of that, really was about primary movement, one of the two forms of drift, just to wind your head back to it. Let's talk about secondary movement or volatility. This is a whole other category where primary movement happens at the time of spraying. If you'll recall, secondary movement can happen long after you've gone home. So, what is volatility? It's a chemical term, and some chemicals, by their molecular nature, are just volatile. It's simply how they're put together. And you know one, it's the greatest example of volatility, it's water. Water is highly volatile. We know that it converts from a liquid or even a solid phase to a vapor phase, just because of temperature alone. If you don't believe me, boil some water, add heat, and it bounces off into the air. It's a volatile. Now, you may recall, maybe not, I guess this would have been 10 years ago. Man, I got old. We reintroduced dicamba to North America in a whole new form. Maybe you've heard of dicamba. It's an inherently volatile group 4 herbicide. And the United States had some trouble with it, perhaps still do. 10 years ago, they sprayed dicamba on cotton and burned crops all over the place as it volatilized, went into the atmosphere, and, well, went all over the place. And yet, we didn't have the same difficulty here in Ontario. And Mike Cobra, our provincial weed specialist on the field crop side, we all thought temperature was going to play a big role in this, and he did the work. He looked at Little Rock, Arkansas, May, June, and July, and he looked at Elora here in Ontario, and he just compared the temperatures on days that guys might be spraying. In Canada, in May, there was only one day where the pesticide label said, don't spray, it's too hot. We know it's a volatile, and the hotter it gets, the more likely it'll volatilize, so that's the threshold. But there were 6 days in Little Rock that were hotter. In June, Elora had 2 days where it would have been too hot to spray. Little Rock had 24 days where you needed to pack in the sprayer, and if you had the bad luck of trying to spray in July, and by the way, we sure don't recommend that in Ontario either, just no chance at all. 31 days out of 31 days too hot to spray. So is it any wonder that they had problems with volatility and drift? And if you're thinking, well, I thought this stuff was like greatly reduced in drift? And the answer is yes. Our current dicamba formulations do have less potential for volatility. That's not no potential for volatility, and this is going to matter. There's Banville Original. That was the original formulation of dicamba, and it was awful. It volatilized just as quick as you'd look at it. So we're going to say that's 100% drift. Just whatever it was, that's 100%. They released Banville 2, and it was a lot less volatile, only about 25% of what it originally was. And Ingenia, Extendamax, the new dicamba, it's only about 5% as volatile as the original, but it's still 5%. And the reason we care is because of its potency. This stuff, a whiff will do you. Imagine you have 1 cup, just a measuring cup. You reach into a 1,200-gallon sprayer. I don't know why you do this. Please don't. And you pull out 1 cup of that spray mixture. That is enough dicamba, if you were to spray it on conventional soybean, to injure it. You may not cause yield loss, but you're going to see it curl up. That's a phenomenally small amount. If you were to dip, say, 2 gallons out of there and spray it, you're going to get a significant yield loss on soybean. That is conventional or IP beans that don't have the trait. It's funny. We end up creating dicamba so guys can spray soybeans, and what's the one crop that's hugely susceptible to drift and burn? IP beans. And if they're flowering at the time, that makes them particularly sensitive. Just 1/100th of the use rate will give almost a 10% yield loss. That's some potent. Again, Mike Cobra and I tried to illustrate this a couple years ago at a meeting. That bottle on the left filled up with, I think it's just Kool-Aid or dyed water, whatever. Let's say that's a full sprayer. That's your 1,200-gallon sprayer filled to the tippy top. Let's say you had been spraying Callisto. This is another herbicide. And you lost your mind and forgot that you still had a third of the tank full of this stuff when you went and sprayed sensitive beans. That would cause a 10% loss. Let's say you had Roundup and only 6% of the tank was full and you forgot it was in there. That is going to cause a 10% loss in beans. Then we have Extendamax, the dicamba. Look how diminishingly small the trace amount that needs to be left in the tank to cause that 10% loss. And here's a little secret. That's actually fake, by which I mean we only had to put a couple of drops from an eyedropper in there to represent the actual volume. But during the demo, people thought it was completely empty. And also it kept blowing away. So we just had to put a little more in there just to let people know that there was something in there at all. Right. So there's product choice and its molecular nature and its inherent properties that if it gets warm, it just evaporates and blows all over the place. But blows where? This is another one of those things where it's not just one culprit. It takes a few people to, or a few factors to create real volatile drift, and that's atmospheric stability. So this should come as no surprise. By now, I'm hoping I've beaten this into you. If you spray on a windy day, you're going to get primary movement, physical drift. But I will say that we do vilify wind. Oh, don't spray when it's windy. Well, hang on a second. Maybe don't spray when it's so windy you have to chase your hat. But maybe a little wind's okay because we can predict where that spray is going to go. We can plan for that. If we have a sensitive crop downwind, put it away. If the sensitive crop is upwind, well, here's a fun fact about drift. Particle drift does not drift against the wind, nor does volatile drift or secondary drift. The wind will always carry it in that direction. In fact, with a little bit of wind and something called convection, we can reduce the impact of off-target drift. It just spreads out over so big a volume that it's not quite as bad anymore. You may have heard this called dilution is the solution. So think of it like this. On any given day, if you've lived on the planet and looked around, you know that cold air sinks warm air rises. Warm always goes up and cold always comes down. So if you spray on a warmer day, then any pesticide that remains hanging in the air will get caught up in these convection bubbles, almost like a lava lamp, and lift up into the air into the colder layers and spread out and just disperse so much that there's simply not enough dose left to cause any trouble. But there's a situation called an inversion. In this bizarre situation, I guess not so bizarre, it actually happens every day to some extent, you get a situation where the cold's on the bottom and the warm's on the top. The warm air won't sink, it just wants to rise, and the cold air won't rise, it just wants to sink. So relative to one another, you get a kind of a layering. Now, if you spray in this, any of those floating particles that you release, the ones that hang around forever, they're not going to disperse or convect. They're just going to hang there. And fun fact about air, it moves like water. That layer will pour downhill. This is why we see fog in gutters on some days. It can be cooler in there. That's where all the cold air pools and the water vapor ends up forming water again. Boy, I didn't say that right. But I don't get two takes on this recording, so you're just going to have to forgive me. That's your inversion. And that's why spraying in a little bit of wind during slightly warmer temperatures creates the convection and the directional drift we can work. And when do we get an inversion? Imagine this is a clock. We got midnight at the top, there's your full day, noon at the bottom. Generally speaking, about an hour after sunrise, the sun will warm the ground, warm those layers, cause convection, and break up an inversion. And into the evening as the sun goes down, all that heat leaves the earth and it creates a relative cool area just along the top of the ground. Cooler at the bottom, warm on the top. Your inversion begins to build. So about an hour before sunset, put the sprayer away and don't be in such a rush to be spraying first thing in the morning when the sun is down. And there's a lot of people out there that ignore that because they've got to get her done, and I get that. But spraying is always compromises. Knowing what's around you, knowing what you're spraying, understanding whether or not you're in an inversion, whether it's even a very strong inversion or how long it lasts, even knowing if there are bees around. All of these things need to be factored in. Off-target drift is something that we have to live with, and the more you understand, the more you can work with it for the lesser of two evils. Now, just to show you what volatility can do in an inversion, we're going to call this a bad combination. I go to what Richard Anderson and his student Hope Long did in 2017. In Thamesville, they did something very cool. They went out to a paintball course and bought one of the smoke bombs. And they set it up on a sawhorse, as you can see here. And the smoke is meant to be a surrogate for vapor. Actually, I think the smoke particles are bigger than vapor, much bigger, in fact. But they're a good indicator. And this worked out so well that they strapped them onto a boom of a sprayer and drove at spraying speed just to see what happened. So what you're about to see is a video. It's going to seem like it's over. It's not over. Stick with me. This sprayer drove down the field, turned around, and came back. Somewhere in there, 90 seconds elapsed. That's how long these cans make smoke. Actually, I think he got most of the way to the end of the field and turned around, and by then it was done emitting smoke and just drove back. The wind was only 1.2 miles an hour at the best, which meant very calm, really calm. Calm is an indication of an inversion, by the way. Then they left the camera running for 52 minutes. They ended up seeing this stuff move over a mile away. I just want you to watch. Shoom! Sped up, because we're not going to sit here for 52 minutes. Turns around, comes sailing back. Hello. And now we wait. Now there is a light wind. It's moving from the right of the screen to the left. And you can see this light, we'll say volatile, just slowly moving downwind, relatively calm, not in any particular rush. When back it comes. Now it's moving from left to right. What is going on? You're home having coffee. The air was moving in the right direction you planned for. Oh, no, it's okay. It's going from right to left again now. That's nice. In fact, it's going to change a bunch of times before we're done. So even if you planned your day perfectly, I'm spraying a volatile, and I want this light wind moving away from this guy's tomatoes. And you did a great job in making those choices, except you sprayed during an inversion when it was very calm and layered, and that wind, however faint, can change direction. In this case, that cloud changed direction a bunch of times over the hour, and it ended up leaving the field in the exact opposite direction that the wind was blowing when they sprayed. And how are you going to control that? So the best thing to do is just know what an inversion is and simply don't spray in it. And I don't want to imply that only volatiles move in inversions. We know from the beginning of this talk, tiny droplets, they also hang forever. They can act very much the same way a vapor can. So spraying in an inversion at all is a bad idea. And you can tell if you're in one several ways. I don't know if any of you are campers early in the morning. Maybe you can hear people talking quietly, and then you come to find out that's from a tent half a mile away. Sound will bend in an inversion layer. It's what makes that train that you rarely ever hear sound so loud some nights. Dust will hang in the air in an inversion. There's no wind. So if you're driving out on a dirt road to do a job or just happen to notice and you can see where you've been because the dust is still hanging there, you're probably in an inversion. If it's really humid, you may not be in an inversion. It kind of slows down the intensity. Cloud cover at night, that bounces radiation back to the ground. It never lets the inversion form. You never get a cold layer. It's like a microwave. And of course, wind. If it's windy, you're probably not in an inversion. It'll stir the layers up. And if we have wind, light wind, we know where the product's going to go, as long as it keeps going that way. So all this to say, sunny days with a light breeze, that's the way to spray. And if all that's too confusing, well, there are apps. I generally don't like the apps, the reason being they draw their meteorological data from an airport miles away, at the top of an air traffic control tower. So we're talking about the temperature at boom height, 20 inches off the ground, and somebody 5 miles away is telling you what it is on the top of an air traffic control tower. It has no bearing. The best way to know what your weather conditions are to get out of the sprayer, walk around to the boom with a little handheld wind meter, and just see what your local conditions are. They could be completely different from what this app might say. We're getting near the end. You're doing well. I will talk about one of the other factors of volatility that made it so bad, the dicamba in the States, and that's a concept called community drift. And it was Mary O'Brien, who goes by Sprague Drift Girl down in Australia, that coined the phrase. We had her visiting, and she said it's kind of like this. You know what? I'm not going to do this to you. I'm not going to do this to you. Just imagine you have 10 operators, and each spray a little teeny bit. And those little teeny bits, in and of themselves, don't represent a whole lot of pesticide loaded into the atmosphere. But because it's a volatile, and there are 10 of them, they all kind of meet together in the atmosphere and pile up. So once all those products pile up in the atmosphere from all those different operators, and then the wind shifts direction, everybody contributes a little bit to wherever it goes. And whatever poor organic grower, IP bean grower, or someone who's growing something that doesn't have that resistant trait gets fried, whose fault is it? Often they find the person who sprayed most recently and is closest upwind, but it may not have just been that person's fault. It was everybody. Everybody contributed a little bit. That's what makes it so hard to figure out where volatile damage comes from, or who to blame, I suppose. Dr. Kevin Bradley, who's a well-known weed biologist out of the States, he basically said the more you use a resistant trait to something like dicamba, then the more environmental loading you're going to get. And the more environmental loading, the more a secondary movement. Period. So the more you use the product, the more drift. It simply can't be stopped. So don't pretend to be surprised. Okay, you guys are doing great. 48 minutes in. I wonder if anyone's still in the room. Let's go to the summary. And for those of you who remember me asking you to remember three things, since Tom Wolfe helped me with well, he didn't help. I liberally stole some of Tom's ideas for this with his permission. I'm going to attribute him to some of this summary. First thing to remember, pesticides move in the atmosphere, and they're rapidly diluted by mechanical and especially thermal turbulence, wind and convection. That's why we like to see spray applications on sunny days with a nice, predictable light breeze. It moves the spray in a predictable direction, and it dilution is the solution any drift rapidly along the way. We can minimize the impact of particle drift using measures like lower booms, protective shields, if you can find one that doesn't weigh a ton, slowing down, and using coarser sprays. And if we can avoid using a volatile chemistry, then we should, because it's always going to move. But if you must, avoid hot days to minimize the risk of vapor drift. And I don't care if it's volatility or particle drift, don't apply pesticides when the atmosphere is stable. That's an inversion. That usually means from just before sunset in the evening till just after dawn, and it tends to occur clear night. So you did it. You survived 50 minutes of me rambling at you. If this was all too much, and I guarantee if you've never thought about it before, it can be overwhelming, I've got some resources for you. This is the first one, working with the OFA, the Ontario Fruit and Vegetable Growers Association, and Crop Life. I think GFO should have been on here too. I wonder why they're not. Anyway, we came up with a website called bedriftaware.ca. It's just a summary of articles, videos, everything you never wanted to know about pesticide drift. And I like it. You can go check it out if you're an operator, if you know an operator, if you know someone that worries they've been impacted by drift, they can learn from this. But it's really just a repackaging of information that Tom and I have written over many years, and we make it freely available to anyone that has the courage to go read it. It's called sprayers101.com. We've got over 350 articles on safe, effective, and efficient use of pesticides. We fancy ourselves comedians sometimes, but I confess it's dad humor, so it's kind of cringy. But we've got a comic book out there called Micron Woman, including videos. We got 15 what we think are goofy videos explaining different concepts of pesticide application. There are books, whatever you never wanted to know. Lots on drones in the last few years too, if that tickles you. So I encourage you to go. It's completely free, and it'll help you learn more about safe, effective, and efficient application of pesticides. So with that, look at that. 51 and a half minutes by my reckoning. May even get you out the door 10 minutes early. Thanks for your attention, and I hope you remembered three things. Bye-bye.